All right, so we have these formulae for different shapes to find the moments of inertia for different shaped objects, and you'll have this for any upcoming quizzes, any upcoming tests that you'll have in the class. So, for example, here's the hoop or the wheel of radius r, and we showed that moment of inertia is equal to mr squared. If I have a cylinder that's rotating about this axis, its moment of inertia is 1/2 mr squared. Here's a thin rod. Here's a cylinder of radius r. But now instead of rotating about the axis through the center, we have an axis going like if this is a person, it would be like through the waist. And then we have a solid and a thin walled sphere. And notice that all the expressions for the moments of inertia are different. And it's because you have to go through and do an integral for each of these to sum up the contribution of all the different mass elements within the objects in order to find their total moments of inertia. Now, let's do a problem where we have two different shaped objects that are coming together. And anytime you have two different shaped objects, say, for example, you have a sphere and a rod that are engaged on an axis that's rotating, this actually happens quite a bit. For example, if you engage a flywheel on an engine, it will change the moments of inertia of the engine or of the shaft that's turning. So let's say that we have two different shaped objects that are coming together and rotating on the same axis, and we want to figure out what is the total moments of inertia. Then we'll just take the moments of inertia of one object and add it to the moments of inertia of the second object. I have a little clip here. This is from The Toy, which is a movie from the 1980s with Richard Pryor. And in the clip, he rotates on the Wonder Wheel, which is this wheel that you can attach yourself to. And we're going to treat this as two different shapes. And I want you to think about as you're watching it, what are the two different shapes that are in this table that we just looked at that we can treat each object as, and then figure out what is the total moments of inertia. So let's go ahead and watch the clip. You'll watch the whole clip, but it's only a couple minutes long. You can watch it here. Okay, so in this clip, we had Richard Pryor, and he was on this wheel. We can treat the system as a hoop, which is the wheel, and as a cylinder, which is going to be Richard Pryor, with the axis of rotation through the center. Right, so if we were looking at this table up here, we would treat Richard Pryor as this object, and then the Wonder Wheel would be that object. Okay, so we can make some assumptions about the mass and the radius of each of these. So if this is Richard Pryor, we're going to treat him as a cylinder. That cylinder will be about the height, which is going to be 2 meters. And in our table, that is going to be our length B. So if you look back at that table, it says that the length of the cylinder is B. And then the radius of the cylinder, which is R, is going to be the distance from here to here, which is the distance from, the center of his neck out to his shoulder, which is approximately 0.3 meters, about 30 centimeters, right, for a typical guy. Now, we'll say that the mass of Richard Pryor is equal to 100 kilograms. That's a pretty big person, but he's tall. All right, so, and then we have the Wonder Wheel as well. Wonder Wheel is just made of rubber, but it's pretty big. So we'll say it has a mass of about 10 kilograms. That might be an overestimate, but not by much. And then the radius, well, Richard Pryor is in the middle of it. So the radius of this Wonder Wheel is about 1 meter, about half the height of Richard Pryor. It might be a little bit more than that, but not much. So given those quantities, we can calculate then what is the moment of inertia. And the total moment of inertia will equal I of the hoop plus I of the cylinder with the quantities that we have there. So that's going to be mr squared. So I'll write it up here. Mr squared. That's for the hoop, plus the expression for the cylinder, which is 1/4 mr squared. Given these are for Richard Pryor, and these quantities are for the hoop, plus 1/12 ml squared. See, I just took these from the table. This is also for the hoop, or for the wonder wheel. Then I can put in some numbers there. Let's see. Oh, I'm sorry. No, not. I got this mixed up. So this is for the hoop, and both of these are for Richard Pryor. Apologize for that. Okay. So I have two different components that are coming together, and I'm adding these shapes together. I want to figure out what is the total moment of inertia. All right. So mr squared, that was 10 kilograms, times the radius of the hoop, which was 1 meter squared, plus 1/4 of 100 kilograms. That's the mass of Richard Pryor, times the radius of Richard Pryor, which is 0.3 meters squared, plus 1/12 100 kilograms, times the length of the cylinder, which is 2 meters. That's its height, roughly. And if I plug all this in, I get 10 plus the moment of inertia of the cylinder is 36. That's the combination of these two terms. So that gives me a total moment of inertia of 46 kilogram meters squared. So the point of this is that when I have two objects that are rotating and they come together, then to find the total moment of inertia, I just add them up. And it's as simple as that. And as I said, this is fairly common because, for example, let's say we have a shaft that's coming off of an engine and it's rotating. It has a certain moment of inertia. And then you might engage it in some way with either another shaft or a flywheel, and it has a moment of inertia. And when you engage it, it changes the moment of inertia of the whole system. So this has real applications in mechanical systems whenever you have rotation, which whenever you have an engine produces rotation. Okay, so you can try these concept test questions. This is just finding the moment of inertia. Don't forget that the moment of inertia is equal to the sum of mr squared, and these are just discrete particles. I think there was another one. We'll come back to this.